Okay, welcome to the second lecture of the week. We're trying to keep it keep it going with starting the third chapter here. This third chapter will not be on the first exam that's coming up. It'll be on the second, some future point. And the third chapter is about motion in a straight line, trying to keep things simple at first to keep things one-dimensional, and then we'll branch out into 2 and 3 dimensions. So first of all, for motion in a straight line, we use a combination of what are known as kinematics and dynamics to study motion in a straight line. Dynamics mostly concerns the causes of motion. Kinematics describes motion in terms of time, position, velocity, acceleration, and so on. Actually, as it turns out, kinematics will be what we spend most of our time on in analyzing motion. Kinematics can be used for motion in 1 or 2 or 3 dimensions, but we're going to stick with 1 dimension for this chapter, just to keep things simple, like I said. An example of one-dimensional motion would be, say, a train moving along a train track. And as long as the ground is level and the track is straight, then the train is only moving in 1 dimension. Even if the train stops and starts backing up, it's still only 1 dimension. Now, if the track is going up a hill, that brings in a 2nd dimension. If it goes around a curve, that would also bring in a 2nd dimension. And if it's going uphill while going around a curve, that would bring in 3 dimensions. So we're not going to go there yet. We're going to keep it simple with just 1 dimension, like a train traveling on level ground in a straight line, that kind of thing. The first section deals with position, displacement, and average velocity. So first of all, we need to define what we mean by position. That's the location where the object of interest is, but we need to define that more scientifically than just saying where something is. An object in motion in 1 dimension, its position is its x coordinate, or whatever coordinate you're choosing to use as the coordinate for that 1 dimension. We usually use the x coordinate for motion horizontally, but of course you could also be moving in 1 dimension going up or down, like for instance something being dropped. That's a fairly common occurrence in physics. And that 1 dimension would often be denoted as the y direction rather than the x direction. But anyway, the position would be given by its coordinate in whatever axes you're using. So generally, x direction if you're going horizontally, y direction if you're going vertically. And its coordinate will be given at a given time, and it needs to be relative to something, because absolute coordinates by themselves don't really mean anything. So usually the coordinate would be given relative to the origin, that is the 0 point on the x line. Or if it's a practical example of, say, a train moving along a track, then you might give its position relative to stationary objects on the earth, like the station, or a big rock or something like that. Stationary landmarks are most convenient because they don't move, but there are some cases where it's usually actually more convenient to define the motion or position of something relative to something which is itself in motion. So, like I said, with the train, you're probably going to define the position of the train relative to something like the station. But if you're defining the motion of, say, a person walking up and down the aisle on the train, and it's a passenger train, so there's an aisle down the middle, then you're probably going to define that person's motion relative to the train, even though the train itself is in motion. You could define the person's motion relative to a stationary object on Earth, like the station, or something like that, but it would become more complicated because you'd have to take into account both the motion of the person relative to the train and the motion of the train relative to the ground or the station. So it's often more simple just to define the motion of something relative to something that's moving, like in that case. Displacement, as we've talked about before, is a change in position relative to a frame of reference. It's the net or straight line distance traveled from the original position to the final position in 2 or 3 dimensions. In 1 dimension, you usually think of it more as the net distance with direction specified relative to the starting point. And displacement can be negative because, remember, positive and negative refer to directions. And so displacement can be negative because displacement is a vector and vectors have direction, which can be positive or negative. Distance, remember, is a scalar quantity and it has to be positive because distance only has a magnitude. It does not have positive or negative in order to indicate direction because being a scalar, it doesn't have a direction. And so distance is always positive. Displacement can be positive or negative. You can potentially have multiple displacements within a given period of time. And that would be, for instance, traveling back and forth. If you travel from Buffalo to Rochester and back to Buffalo and then to Batavia, that's multiple displacements within that, say, 2.5-hour period. And the total displacement would just be the sum of all the individual displacements. Okay, so we can see equation 3.1. Displacement is just the final x position or the final x coordinate minus the original x coordinate. It's also called delta x sometimes. Delta, which is drawn as just a triangle, is the Greek letter which is often used to mean change in. So delta x is change in position. And the SI unit for displacement would be meters. But any unit of distance can be used. So it could be centimeters, or it could be inches, or feet, or miles, or whatever. The total displacement will be delta x total, T for total, and that is just the summation of all of the individual displacements, which is what this means. So for instance, if you start at x equals 0 and go to x equals 2, and then turn around and go to x equals minus 2, there will be 2 segments in that overall total displacement. Segment one will be where you go from 0 to 2, and delta x for that segment 1 will be the final x value, or that final x coordinate for the first segment, minus the original x coordinate for the first segment. And that's 2 minus 0, because you started at 0 and ended up at 2, which is 2. Then you have the second segment of the movement where you are at x equals 2, and you turn around and go back to x equals minus 2. And the displacement for the second segment will be the final position, or the final x coordinate for the second segment, minus the original x coordinate for the second segment. So that's going to be minus 2, because that's where you end up, minus positive 2, because that's where you started out for the second segment of this little journey here. And negative 2 minus 2 is negative 4. So that's the displacement for the second leg of the journey. Because you went from positive 2 down to negative 2, that's a difference of 4 in the negative direction. And so the total displacement is going to be just the first displacement plus the second. That's 2 plus negative 4, which is negative 2. Because you end up at negative 2 and you started at 0, so the overall displacement is minus 2. Okay. All right. Moving on. we can talk about average velocity. Velocity is just the displacement divided by the time period over which the displacement occurs. And velocity is a vector, as we've discussed before. And so it does have a magnitude and direction. And because of that, velocity can be negative. So velocity, as we said, is displacement divided by time. You can think of it as the rate at which the position changes over time. So you've got a position, and then you have a new position, and it took a certain amount of time to get from one position to the other. And the change in position divided by the amount of time it took to go from one position to the other is your velocity over that time period. So each position of an object, if we're following its movement, and we'll call each position xi, has a corresponding time, and we'll call that ti. So it's, it's at a certain location at a certain time. So it might be here at time 1, and it might be here at time 2. So each of those positions has a corresponding time. We can calculate the velocity for any given part of the journey. So if the object moves from point 1 to point 2 over a certain period of time, we can calculate the velocity for that part of the journey. If it then moves to point 3 over a certain period of time, we can calculate the velocity for the entire journey from point 1 to point 3, or we can calculate it for just the part from point 2 to point 3. So we can calculate the velocity for a given part of a journey or the average velocity for the overall journey. Average velocity is symbolized by v with a line over it. When you put a line over something, that generally means average. So v average is just the total displacement between 2 points divided by the total time elapsed between the 2 points. That's often written as delta x over delta t. That is change in x position over change in time. Or in terms of individual points, it would be the final x position minus the original x position divided by the final time minus the initial time. A lot of times the initial time will be 0, which makes things a little easier, but not always. The average velocity is a vector, like any kind of velocity is, and it can be negative. But again, negative tells you the direction, not the magnitude. The SI units for velocity, well, displacement, the SI units are meters, and time, the SI units are seconds. So you would expect the SI unit for any kind of velocity, whether average or instantaneous, to be meters per second. And that's what it is. So an example of using all of these individual segments of a journey to find out the displacement for each segment and the displacement overall would be example 3.1. And I'm going to simplify it a little bit by just saying Jill is delivering flyers. She traveled east for 0.5 kilometers, and that takes 9 minutes. And then she returns home, which is the same distance in the opposite direction, but it takes the same amount of time. Then she heads east again for 1 kilometer. That takes 15 minutes, and returns in the direction of home, that is west, for 1.75 kilometers, which takes 25 minutes. And then she stops to rest. What is the total displacement at the end? That is when she stops to rest. And we want to know also the magnitude of the final displacement and the average velocity for the entire trip, which we can get from the total displacement and the total time. And what is the total distance traveled as opposed to displacement? Okay, and then we can graph her position versus time if we want to. probably more important for figuring out the question, it would not be a bad idea to write out a little diagram like I did here. Here's Jill's house. Oh, I forgot the little chimney with the smoke coming out of it. Okay, there's the chimney with the smoke, and a little door and a little window, and some flowers in the garden, maybe. And also, we can sketch out her movements. From home, she goes 0.5 kilometers east, which I'm going to represent as being to the right. And it took 9 minutes. So here's the 0.5 kilometer point. From there, she turned around and went home 0.5 kilometers to the west. And that's also took 9 minutes. Once home, she gathered up more of her stuff and went to the east again for 1 kilometer. So here's the 1 kilometer point. And you notice the 1 kilometer point is just about twice as far as the 0.5 kilometer point. I'm trying to do things to scale, reasonably anyway. And that took 15 minutes. And at that point, she turns around and goes 1.75 kilometers to the west. And that takes 25 minutes. So we're going to choose east as the positive x direction and west as the negative x direction, which is the conventional way of doing things. And we can divide up the journey into the 4 segments. For segment 1, her original x position was at 0. We're going to call her home 0. Okay, so she started at home, so that x original would be 0, and x final would be 0.5 kilometers. The time it took would have started at 0 time. They didn't really say that, but okay, you could pick a time if you wanted to, but 0 is the easiest time to pick, so I'm going to call it 0 time. And the final time for that part of the journey would be 9 minutes. And the direction is positive, or east. The second segment started at the 0.5 kilometer mark and went back to 0. So it starts at 0.5 kilometers and ends up at 0. The beginning time for that would have been 9 minutes because she immediately turned around and went home. So it was at 9 minutes till she turned around and went home. It took 9 more minutes to do that. So that would be 18 minutes at the end of that part of the journey. And the direction was negative or west. For the third segment, she started again at the 0 point, which is home, and she went 1 kilometer. And so that would be the final point for the third part of the journey. The time would have been, assuming it took 0 time for her to gather up more flyers, assume they were sitting right by the door so she could just grab them and go. She would have started the third segment of the journey at 18 minutes, and it took her 15 minutes, so 18 plus 15 is 33 minutes is when she would reach the 1 kilometer mark. And that's in the positive or east direction. The fourth segment of the journey starts at the 1 kilometer mark, and it ends up at the negative 0.75 kilometer mark because she went backwards 1.75 kilometers. So 1 kilometer to the west takes her back to the 0 point, but she's still got 0.75 kilometers to go beyond that. So she ends up at negative 0.75. All right. She started that part of the journey when she was at the 1 kilometer mark, which was 33 minutes. And it takes her 25 minutes to do it. So 33 plus 25 is 58 minutes. So that's when she reaches the end of the overall trip. And that was in the negative. This last segment was in the negative direction, or west. So for part A, if we want the total displacement at the end, we take delta x1, that is the displacement for the first leg of the journey, plus delta x2 with the displacement for the second segment of the journey, and so on. And that's just final x minus initial x, or original x. So the displacement for the first leg of the journey was 0.5 minus 0, which is 0.5. The displacement for the second leg of the journey, though, is 0 minus 0.5. Because remember, she ended up at 0, so that's the final position. She started at 0.5, and it's final minus initial. So it's 0 minus 0.5, which is negative 0.5 kilometers displacement. The third leg of the journey, the displacement is the starting point, or sorry, the final point minus the starting point. So the final point would be 1 kilometer, and the original point was 0. So that's 1 minus 0, which is 1 kilometer. And the fourth segment started at 1 kilometer right here, and it ends at negative 0.75 over here. So if you take final minus initial, it's going to be 0.75 minus 1, or sorry, negative 7.5 minus 1, which is negative 1.75 kilometers for the displacement for the fourth segment. And there is no fifth segment, so ignore that. So the total displacement is going to be the sum total of all of these, the displacements for the individual steps. And that's what this is. Summation of delta xi just means add up all the displacements. So that's delta x1 plus delta x2 plus delta x3 plus delta x4, which is 0.5 plus minus 0.5 plus 1 plus minus 1.75. And that leaves us with a displacement of negative 0.75 kilometers overall. As you can see from the diagram we drew, she ends up negative 0.75 kilometers from where she started, which was 0. So that makes sense. And this is just a way of doing it without having to draw out a diagram. There will be any number of problems where the steps are, where there are so many steps or the steps are complicated enough that you might not want to draw them out. So drawing it out is one way to do it, but doing it mathematically is the other way to do it. So for B, we wanted the magnitude of delta x total. That is the magnitude of the total displacement, which will be just the absolute value of negative 0.75, which is 0.75 kilometers. The average velocity is, again, total displacement over total time. We just found the total displacement, which was negative 0.75, and the total time was 58 minutes. That is all of the times for all of the segments added up. So negative 0.75 kilometers over 58 minutes gives us a velocity of negative 0.013 kilometers per minute. Those are in the units that we were given. If you wanted it in SI units, then you would have to take kilometers per minute and change it to meters per second. You can change minutes to seconds by taking kilometers per minute, and remember that minutes is in the denominator, so you want the relationship is 60 seconds per minute, of course, or 1 minute for every 60 seconds. You'd want to use it in the latter form because you want minutes in the numerator so that they will cancel with minutes in the denominator. And now you would have kilometers per second if you stopped there and wrote the answer down. But we want meters per second, so now we have to convert kilometers to meters, and 1 kilometer is 1,000 meters, or there are 1,000 meters for 1 kilometer. Here we know that we want kilometers as the unit on the bottom and the conversion factor because it has to cancel out with kilometers in the numerator up there. And so now we have meters per second as the units. And that would be negative 0.216 repeating meters per second. Okay, so if you wanted it in SI units, that's how you can get it there. Part D is the total distance traveled, which is basically the total distance regardless of direction, which means add up the absolute values of all of the displacements. So absolute values of displacements. That's what you want. So it'll be the absolute value of 0.5 plus the absolute value of negative 0.5 plus the absolute value of 1 plus the absolute value of negative 1.75. And when you add up that all up, you get 3.75 kilometers. That's the total distance back and forth and back and forth. Okay, so you can also get it from going back to the diagram. 0.5 plus 0.5 plus 1 plus 1.75 would give you a distance of 3.75. If you want to graph her movements in terms of position versus time, you could do it like this. Basically, she starts at 0. At 9 minutes, she's at 0.5 kilometers. At 18 minutes, she's back home at 0. At 33 minutes, she's at 1 kilometer in the positive direction. And then at 58 minutes, she's at negative 1.75 kilometers versus the original position. And so it would look something like that. Okay. And that's the end of that example. And that's also enough time for this segment. So I'm going to stop here and we'll continue on in a moment.